So, the first part of the project, and it's all just game, we're just talking about game probabilities and game. Okay, in the first part of the project, there's 4 parts of the project, and each part has 2 parts. The first part is experimental, where you conduct an experiment doing the game. And the second part is theoretical probability, where you're actually explaining the logic behind where you get your probability based on all total possible outcomes. So the first section of the first part of part 1 of the project, there's not 2 parts of the project, there's 2 projects, part 1 project and part 2 project. The first one, we're talking about rolling a 6-sided dice. Obviously, a 6-sided dice in itself explains how many possibilities there are. 6. Okay? So there's 6 possibilities. So if we want to know, this is the first section, this is an experiment. We're going to conduct an experiment to find experimental probability. Experimental probability is the number of occurrences out of the total number of possibilities. In other words, let's say the first question that's asked is, how many times are you going to conduct this experiment? All right, so how many times are you going to roll the die? In this case, the first one, we're rolling a 6-sided dice. How many times are you going to roll the die? So the first question is, how many times? It's got to be greater than or equal to 50. So let's just stick to 50, okay? So I'm going to roll this 50 times. Of the possibilities, what are those possibilities? If you want to look at it from the perspective of what's on the dice, you've got a 1, you've got a 2, you've got a 3, 4, 5, and of course, a 6. So if we roll it 50 times, we just make tally marks on the number of times we roll it. So the first roll, I roll a 2, I'm going to mark a 2. Second roll, I roll a 4, I'm going to mark a 4. Third roll, I'm going to roll a 4, I'm going to mark a 4. Now, I'm not going to do this 50 times, but I'm going to simulate like I did. You can roll it, or you can use the links on the direction to random.org where you roll 1 die. Okay? So let's just say I rolled it 15, that's 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 20, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Okay? So, we rolled 50 times. We got a 1, 8 times. We got a 2, 7 times. A 3, 10 times. A 4, 10 times. A 5, 7 times. And a 6, 8 times. Okay? That's our experiment. That's all it asks you to do. This is the number of times, which can also be said the frequency of rolling a 1 out of the 50 times. We roll it 8 times out of 50. So if we rolled it 8 times out of 50, what do you think our probability is going to be? Experimentally, the probability of rolling a 1 on our 50 tries is 8 out of 50. This is our probability. Probability of rolling 1 is 8 out of 50. Guess what? 7 times out of 50, that's 7 out of 50 for rolling a 2. 10 out of 50 for rolling a 3. 10 out of 50 for rolling a 4. 7 out of 50 for rolling a 5. And 8 out of 50 for rolling a 6. Now, if you want to make percentages, remember 50 is half of 100, and percent is simply out of 100. So we just multiply that number by 2 to get us our percentage. This is 16%, 14%, 20%, 20%, 14%, and 16%. And if you add those numbers up, they should come up to 100. Okay? That's the experimental part of it. That's the easy part. We just conduct an experiment, write down our data, and collect the data, and conjecture what the probability is based on our actual experiment. Now, the theoretical part, which is part B, they ask us what model. Okay, what model do we use? And they give you an option, tree diagram or an area model. Now, I don't know if you noticed this, but the second part asks you to tally not tally, but what are the theoretical probability of getting one of these numbers out of 6? If there are 6 sides of a die, 6 sides, and they're all the equal size of the dies, and the weights are like the center of gravity is in the center, we can say that each number is equally likely. That is the basis of theoretical probability. Theoretical probability is based on equal likelihood. So all things created equal, each one of these numbers should come out 1/6 of the time, because there's 6 sides. 6 equal sides, 6 equal probabilities. 6 equal probabilities out of 100 is like 16.7%. I don't know what it is, actually. I think it is that. But yeah, it's 1/6. That's our probability. That's based on theory. Model used? Here's your area model right here. That's an area model. Make sure that when you create it, all the cells are the same size, because the basis of an area model is based on the fact that if all things are created equal, each one would have an equal opportunity. Here's a good way to think about an area model. You ever been to those carnival games where they have a bunch of spaces and you're given a coin, you have to throw it on a specific colored square to win? That is exactly an area model, okay? Now, some of the squares are bigger and some of the squares are smaller, but the whole point is each one has a specific area that it's supposed to, it takes up some of the area of the winning space, okay, of the playing space. But this is an area model. That'd be like tossing a coin into it. If they all have equal likelihood, you have a 1/6 chance of hitting each one, right? Okay, so we could use an area model. That's our theoretical probability right there. What's the probability of rolling a 1? 1/6. Really, this is it for part 1. It's that simple. That's it. Part 2 is 2 coin flips, right? Mm-hmm. You're going to conduct an experiment. Take 2 coins. I don't care what kind of coins you do. Random.org has 2 quarters. I have 2 pennies. Each penny has a head and each penny has a tail. Guess what? You're going to flip it. This is part 2A, which is experimental. Flip 2 coins. What are the possibilities, total possible outcomes of flipping 2 coins?
You can get heads, heads, you can get tails, heads, heads, tails, and then tails, tails.
That's right. So how many heads do you get if you flip 2 heads? I just answered it, didn't I? This is 2 heads, right? Out of the 4 possibles, right? That does mean 2 heads. That's 1 out of 4 possible outcomes. 2 heads is 1 out of 4 possible outcomes. This is 1 head, also 1 out of 4 possible outcomes. I'm going to write the same exact thing here. 1 head, which is 1 out of 4 possible outcomes. I know I'm writing a lot, and it's a lot of the same stuff, right? This is no head, 1 out of 4 possible outcomes. Now, I go to this much trouble to write all this down because I want you to figure this out. I'm going to conduct an experiment. I'm going to flip coins. How many heads do I have if I roll? How many possible head combinations are there? 2 tails is 0 heads. Either one of these is 1 head, and 2 heads is 2 heads, right? So, number of heads on the flip, okay? So I'm going to flip these 2 coins 50 times. Got to do it at least 50 times. It asks me. Greater than 50. Greater than or equal to 50 times, all right? Number of flips. It's going to ask you, that's the first question, number of flips. It doesn't ask us how many times you're going to conduct this experiment. So, I'm going to start. I got 2 heads. That goes under 2. Now I'm going to do it again. This time I got 2 tails. No heads. I'm going to do it again. Got 2 heads. I'm going to do this 4 times. I got a head and a tail. Coin 1 is a tail. Coin 2 is a head. It's still just 1 head, right? So we'll continue this process until we get to a point where we have 50 experiments conducted. Okay, so in our experiment, we find that out of the 50 rolls, number of heads on a flip, we got 13 that were no heads. We got 22 that was 1 head, and we got 15 that was 2 heads. So what is the experimental probability? And I'll write it like this, probability with an E as your... It's just describing what kind of probability it is. The E is your subscript. Probability experimental for 0 is 13 out of how many times do we do it? It's the number of occurrences over the number of possible outcomes. How many times do we do the experiment? 50 times. Probability of getting a 1 is 22 out of 50. And the last one is 15 out of 50. So essentially, we conducted this experiment and we came up with some information. Now, if you want to do this, this becomes 26%. We're talking about just multiplying by 2, 44%, and this is 30%. Okay? And if you add these together, you should get 100. All I did for the percentages, if I conducted the experiment 50 times, I multiply the answer by 2, and that gives me out of 100. Because 50 times 2 is 100. So 50, if I change it to 100, multiply 2 over 2 by this, it's 26 over 100, which 26% is actually Latin for out of 100. So, now we're going to talk about part B of this, which is a theoretical. We already did a lot of it right here. But it tells you, okay, you have a chart that looks like this. First flip and second flip. And each one has a head and a tail. And there's a little block like this. And you got to fill in what's the number of heads. Fill in the number of heads for each combination. So this is just the same thing as this. This is both coins are on heads. How many heads do you see if both coins are on heads? 2, right? How many coins are on heads if the first one's on heads and the second one's on tails? 1, right? First one's on heads, second one's on tails. How about if the first one's on tails and the second one's on heads? Same thing, 1. Last one, if they're both on tails, 0 heads. Now this, everybody, just about everybody that's done this has done this wrong. Right, Grayson?
Yeah.
People have done their experimentation absolutely correctly and then go to the theoretical part and throw their experimental data into it. Read the directions. You need to delineate between the experimentation and the theoretical data. The theoretical probability is completely different, or it should be somewhat, at least similar but different. How can I say that? Because that's what probability is. Your sample size is the number of times you do it in an experiment. The sample size in theoretical has to do with the total possible outcomes. The total possible outcomes for flipping 2 coins is 4, isn't it? There's only 4 possible outcomes, right? If you have 4 total possible outcomes, and you only have 3 ways to get it, you got to think, how many ways can you get 2 heads out of 4? Look at the chart. How many times you see 2 in that chart? Once, right? How many ways can you get a 1 on this chart? There's 2 ways you can get heads, right? So because of that, it's 2 out of 4, or 2/4. 1/2, what do you want to call it? Okay? How about the probability of 0? How many times do you see 0 on this little chart? 1 out of 4. Now, some of you may say, hey, this seems familiar. It should be, because it's binomial probability. Remember when we talked about binomial probability and the guy's at the free throw line and he's shooting baskets? He only has 2 ways to hit a basket, right? He can either make it or he misses it. If you take 2 shots, there's 4 ways you can shoot the baskets. You can hit the first one, hit the second one. You can hit the first one and miss the second one. You can miss the first one and hit the second one, or you can miss them both. 4 ways. But you can shoot 1 basket out of the 2 different ways. Either you hit both baskets, or you miss both baskets, or you only hit 1. There's 2 ways you can hit 1. So half of the shots should be 1 out of 2, and the other shots should be both of them or none of them. So it's the same thing here. When you flip coins, you should get, theoretically, you should get 2 heads 1/4 of the time. You should get no heads 1/4 of the time, and you should get 1 head half of the time. Okay? That's it for this particular part. Part 2 experimental is done right here, given all the information. This is theoretical right here, and that's it. Now the last part, or the third part, not the last part, the third part is drawing cards. Now when we draw cards, we have to know the demographics. I'm writing this down because you probably need to know. Y'all have heard the word demographics a lot. It's the makeup, okay? When we talk about demographics, a lot of people talk about race, and people talk about gender, talk about age. Those are all demographics of a population of people. In this case, we're talking about a standard deck of cards. So what are the demographics of a standard deck of cards? Okay? How many total cards are there in a standard deck? Right, 52 cards. Total. That does not include jokers. No jokers. Alright? How many suits? 4 suits, that's right. We got diamonds, we got hearts, we got clubs, and we got spades. How many colors? 2, right? What are they? Red and black. How many face cards? Right, 16. 4 per suit. Or 16. Because there's 4 suits, 4 per suit means 16. How many number cards? It's 9 per suit, or 36. This is the demographics, all you need to know. It's important, you have to know the demographics of a deck of cards, or you can't do theoretical probability at all. You cannot do theoretical probability. What is the probability, or think about this, what is the number of specific numbers there are in a card deck? So let's say how many 8s are there? 4 specific cards. How many kings? 4. How many aces? 4. Because there's 1 for each suit. Okay? Make sense? I'm not going to write that down because that's pretty much given. Now let's talk about this. Experimental on, this is part 3. We're going to talk about a deck of cards. I just so happen to have a nice little deck of cards right here. And what we're going to do is we're going to conduct an experiment based on just doing it. We have 52 cards in a deck. 26 are red, 26 are black. We have 13 clubs, 13 spades, 13 diamonds, 13 hearts. We have 16 face cards and 36 number cards. Alright, so let's think about this for a second. The first question in experimental probability is, what's the number of times you're going to do this? It doesn't say this, but it says how many times you're going to draw cards. And it have to be more than 50, right? A lot of people are choosing the number 52 because that's the number of cards in the deck. And that's okay, I don't care. But what are you seeking? That's not the question it asks. I'm not sure what it asks. It says, what are you conducting? What are you looking for? Color, suit, face card, what? Well, let's just say we're looking for... I wanted to say one-eyed jacks, but I forgot to give the demographics then. There's only 2 one-eyed jacks in the deck, and I'm not sure. I think they're hearts and spades, or maybe clubs and diamonds. I don't know. That's beside the point. That's very rare. 2 out of 52. But let's look at here. What are we seeking? Let's say we're looking for red number cards. Red number cards. So we're going to conduct an experiment. I'm going to draw out of this deck of 52 cards 52 times. That doesn't mean I'm going to draw and then leave it aside, because that would change the probability of the next draw. But I'm going to draw, and the first card I draw is a red king. Okay? So what I need to do is when I draw this down, how many number of red cards did I put? I don't know. How many cards total? Cards pulled. I'm going to do 50. Okay? I didn't get a red number card. I got a red face card. Then I'm going to shuffle it a little bit. However you want to shuffle. Some people do the old method of just putting them together. I'll do the little hand shuffle thing. And I draw another card. A 9 of spades. It's not a red number card. 5 of clubs. Not a red number card, right? Draw again. 5 of spades again. Look at that. Red 3. So I would do that. That's 6 pulls, and I've only got 1 red card. Well, let's say I pull 52 times. Okay. I did it 52 times. It says 50. I'm going to say 52 cards were pulled. And I got, red number cards, I got 17. Okay? 17 red number cards. Alright? Out of the 52 pulls, I got 17. So what's the probability of pulling a red number card? This is out of experimentation. It's 17 out of 52. Okay? Now, theoretically, we have to look at it from a different perspective. So that's what Part B is always about. Part B is theoretical. Theoretical probability is based on equal likelihood. We keep talking about that. I want to keep drilling that into your mind. Equal likelihood means that all cards are equally, there's an equal opportunity of pulling each card. Okay? So, there's a total number of 52 cards. How many red number cards are there? Well, there's 2. Half of the cards are red, right? How many of the cards are number cards? We said 36 out of 52, right? We said 36 number cards. 36 number cards. 9 pursuit. Well, if it's 9 pursuit, we have to multiply by half, right? So 36 times 1/2 is 18 out of 52. 9 out of 26. We'll just leave it 18 out of 52. Because we can see they're similar, but they're not the same, are they? So our theoretical probability is not the same as our empirical or experimental probability. They're similar, but different. They're close. All right? What do you think might be able to cause this to be closer to theoretical probability? What are some ways we might be able to improve this and be more accurate to the theoretical probability? And why do you think that is? Anybody have any conjecture about this? Because this question is asked at the end of the project. Anybody have anything they want to add? What do you think happens if you do fewer pulls out of the deck? Is it as accurate?
No.
Okay, if it's not accurate if you do fewer pulls,
But
if you do more, then what happens?
it's more accurate.
There you go. That's it right there in a nutshell. The more pulls you do, the more draws out of the deck you do, the closer you're going to get to theoretical probability. This is the same thing when we're talking about statistics. Statistically, when they do things, they try to figure out a sample of the population to determine the demographics or the answers to all the population within a margin of error. That's what statistics is all about, okay? So, we're going into statistics after this project is done, but I don't want you guys to think that anything we do in statistics are required to learn how to find margin of error or any of those things, standard deviation. I'll give you tables. You won't have to calculate standard deviation. Actually, it'll do it on your calculator. But that's part 3. Part 4 is we go back to the dice again, but this time instead of just 1 die, we're doing 2. Okay? So now we're doing 2 dice. And we get a chart that looks like this, and that's theoretical. We'll do it later, but I'm going to show you how to do the experimental probability. Experimental probability is pretty simple. Let's do this thing. I want you to think about what are the total possible rolls on 2 6-sided dice. If there's only 6 possible rolls on 1 die, right? How many possible rolls on the other die? So the total possible outcomes for both dice is what?
12. No, 36.
Why? Because the 1, if you roll a 1 on the first die, there are 6 ways to get the second die, right? If you roll a 2 on the first die, there are 6 ways to roll. So it's 6 times 6. Theoretical, that's true. But we're doing experimental, we're going to roll it 50 times. Now I want you to think about this. We're talking about the sum of both dice. What is the lowest sum of both dice you can roll? The lowest sum of both dice. 2, because the lowest number on both dice is 1. So you can't roll any lower than 2. And the highest roll of both dice is a 12, because you can't roll 1 dice more than 6, right? So we can roll a 2, and any number between 2 and 12. Okay? So what we're going to do is we're going to take 2 die, and we're going to roll it 50 times. Now you can go to random.org. There's links in the project that lets you do it. So I'm going to roll it. My first roll rolled off on the floor, but I rolled a 7, 6 and a 1. All right? So I'm going to tally a 7 here. I'm going to roll again. I rolled a 2, 1 and a 1. A 6. And I'll do this 50 times. Let's just say 2 2s, 6 3s, 10 4s, 11 5s, 17 6s. No, 6 6s. 12, 11, 24, 25. 15 7s, 6 8s, 11, 9, 7, 2. I don't know if that's right, but let's see how that works out. Probably not going to work out. Yeah, way too many. Way too many. Let's go here and here and here and here. Okay? So let's start again. 2 plus 6 plus 6 plus 6 plus 7 plus 2. 29. All right. 29. 40. Okay. Okay? That's 50 rolls. Now I can change this a little bit if I want to. I'm going to go like this. I'm going to say 9. This is 1, and this is 1. So we should add this up. 2 plus 6 is 8, 13, 14, 29, 35, 36, 41, 48, 50. Right? Okay. So this is our experimental. This is what we get on our rolls. Sum of rolls. What is the probability? We rolled 50 times. So 50 times. How many times we get a 2 out of 50? We got 2 out of 50, right? How many times roll a 3 out of 50? 6 out of 50. How many times roll a 4? 5 out of 50. And so on, all the way to 12 where we rolled a 2 out of 50. Now, if you want to change this percentage, obviously all you have to do is multiply this number by 2. So this is 4%, 6%, 5%, 1%, and so on. Okay? That's the glory of doing 50 rolls. Whatever your answer is, multiply 2, you get percentage because it's over 100. All right? Now, theoretically, we have a whole different parameter to look at. We just said, this is part B, theoretical. We know that there are how many? There's 6 sides, 2 by 6-sided dice. Total possible outcomes. 6 times 6, right? 6 times 6, so it's 36. So the probability is the total of occurrence over the total possible outcomes. So, yes, ma'am.
How is that 4%?
Huh?
The 2, how is that 4%?
4 what? The 2? Because 2 over 50 is the same thing as 4 out of 100, right?
Yeah.
Percent is simply that number over 100. 4% is 4 out of 100. 4 out of 100. 2 out of 50, if you multiply it by 2, you get, or 2 over 2, which is multiplied by 1, you get 4 out of 100, right? If 2 out of 50 is the number of times people got a 2 when they rolled it 50 times, if you rolled it 100 times and you got the same ratio, you get 4 out of 100, correct? That's where I got 4%. This 6 shouldn't be 6%, it should be 12%. This should be 10%, I apologize. This should be 2%, and so on. You're supposed to multiply the number by 2, and I didn't do it on the rest of them. So thank you for catching me on that. All right, so on 2 6-sided dice, you'll see a header on the top, says first roll, with the numbers 1 through 6. And then you'll have a header on the side that says second roll for the rows, with the numbers 1 through 6 again. Let me make this bigger so you can see it better. So this column title is the number of the roll for the first roll. And this row title is the number of the roll for the second roll. And what we're asked to do is, what is the sum of rolls for each combination? I'm not going to be able to see that with this. There we go. I don't know how long this one will last. Okay. So look at the first roll and the second roll. On the very top corner, this is supposed to be a 1 right here. What is the sum of rolls if the first roll is 1 and the second roll is 1? 2. That's right. And that goes right here in this intersecting cell. That's the sum of rolls when the first roll is 1, the second roll is 1. What if the first roll is 2 and the second roll is 1? What is the sum of rolls? 3, correct? How about if the first roll is 3 and the second roll is 1? Sum of rolls is 4. We can keep doing this through the entire thing. First roll is 1, second roll is 2, sum of rolls is 3. 4. Okay? We'll keep doing this until we go through the entire thing. This chart that is in your thing people have polluted it with their experimental data, when all they have to do is put in the sum of numbers theoretically with all things equal, right? That's what I'm doing here. I'm just putting them all equal. I'm sorry? What'd you say, Yuliana? Okay. 5 and 1 is 6, 5 and 2 is 7, 5 and 3 is 8, 9, 10, 11. 6 and 1 is 7, 8, 9, 10, 11, and 12. All right. Now, experimentally, we found our information just by collecting data from rolling dice. But theoretically, we don't do it that way. We talk about all things being equal, okay? We're going to do the same thing. We're going to write all the possible outcomes of the sum of dice rolls. 2 through 12. Now I want you to tell me, how many times did we roll a 2? How many possible ways can we roll a 2? There's only one possible way that we can roll a 2. How many possible ways can we roll a 3? How many possible ways can we roll a 4? We can roll the first die 3 and the second roll 1, that equals 4. We can roll the second die 2 and the first die 2 and the second roll 2 and get a 4. Or we can roll the first die 1 and the second roll 4 and get or 3 and get a 4. So one die is a 1, one die is a 3, or they're both 2. Either way, those 3 ways can get us a 4. Guess what? 5, we've got 5 times there, the 4 times there. 6 is 5 times. 7, we show 6 times. 8 goes back down to 5, and it goes all the way down to 12. Now logically, I want you to think about this for a second. There's only one way to roll a 2. Both dice have to be 1. There's only one way to roll a 12. Both dice have to be a 6. If either dice is anything else, you can't have a 12. Okay? The odd number sum rolls have an even number of possibilities, and the even number of sum rolls have an odd number of possibilities. That's not a conjecture, that's a fact. Because the odd numbers, sum rolls, just come out to have that many. Mainly because there's no way you can add 2 dice together and get an odd number. 2 of the same dice numbers together and get the same number. You can't. That only happens once, and only happens with even number sum rolls. Alright, so we see here what the number of times this happens. The next part asks, what's the probability? Well, recall that probability is the number of occurrences over the number of total possible outcomes. Well, how many times does the number 2 occur? Once. Out of how many total possible occurrences? 36. There are 30 total possible outcomes, so probability of 2 is 1 out of 36. 3, there's 3 times, there are 2 times it shows out of 36. 4 is 3 times out of 36. You can go all the way to 7, it's a 6 out of 36, and back down to 12, which is also 1 out of 36. You can fill that in. It's very simple. And at the end of the project, there's 4 questions, and it's asking about the last part of the project you did, the 2 die roll. Describe your experiment. Put in words what you did. I rolled 2 die 50 times, collected the data, realized that my answers, the frequency of the sum of rolls, would give me the probability of that happening out of the 50 rolls. Okay? Now, give me a minute now to explain what I need you to do for part 2. This is the nuts and bolts of it. Part 1 is the nuts and bolts. Part 2 is we're putting everything we did on part 1 into action. So the first thing you want to do is you want to make your rules. Make your rules for your game, okay? So first of all, you got to know what games you're going to play, and you have to know the probability of each. So I'm going to erase the coin flip because I don't want to use coin flip, okay? But I want to keep everything I had from cards and 2 dice because that's what I'm going to use, okay? So let's start with the rules. The rules of my game. Rules. Okay? Pay $1 to play. Okay? That's the first rule. Play, $1 to play. Okay? Roll 2 dice. Okay? Even number sums. No, let's do this. Let's not. That's too easy. Rolls greater than or equal to 9 get to if you roll a number greater than or equal to 9, you draw a card. Less than 9, you lose. Okay? Roll 1, roll 2, this is rule 3. Okay. Roll 4. Rule 4. If you do roll larger than 9, you draw a card out of standard deck. Okay? If card is red face card. Okay? If card is a red face card, win small prize. Okay? If card is a black king, win a large prize. Okay. So we have to do this. Okay, I'm going to one more. If not red face card or black king, you lose. Okay? Those are my rules. Lose gets nothing. Okay? Lose gets nothing. But now we have to calculate probability. We're going to roll 2 dice. What is the probability of rolling a sum greater than or equal to 9? Right here, right? 9. Let's finish this so we can figure it out. What is this roll? So this is 2 out of 36. We have 11 twice. 10 is 3 times. And 4 is 4 times. 4 out of 36. Okay? So we're going to do theoretical first, okay? Probability, theoretical. All right? So, drawing this card is going to be 4 out of 36. It's the probability of a 9 or probability of 10 or probability of 11. So you can just write it like this, probability of 9 through 11. 9 to 12, I'm sorry, 9 to 12. So it's 4 plus 3 plus 2 plus 1 over 36. 4 plus 3 plus 2 plus 1 over 36. That's 10 out of 36, okay? So what that means is that true? No, is it? Yes, 10 out of 36. 10 out of 36 people will get to draw a card. Well, how many people won't get to draw a card? 26 out of 36 will not. Okay? Remember, this is theoretical, okay? Now, if the card is a red face card, win a small prize. What's the demographics of a red face card? What is it? It's out of 52, right? We have 52 cards. But how many red face cards are there? First of all, how many red cards are there? There's 26 red cards, right? That means there's 2 suits in the red card. How many face cards are there per suit? 4. So red face cards, there's 2 suits, 4 face cards per suit, so it's 8 out of 52. 8 red face cards out of a total of 52 possibles. Okay? How about a black king? How many black kings are there? There's a spade and a club, right? You have 1 king per suit, and only 2 suits are black. So that's 2 out of 52 black kings. Okay? So there's your probabilities. 10 out of 36 will go on to actually draw a card, and there's only 2 ways to win, okay? So, what's the probability in theory to win a small prize? Probability of a small prize, and this is out of theory. I'm going to put a T as my subscript to delineate between experimental and theoretical probability. Small prize is the theory that I'll get whatever I roll better than a 9, which is 10 out of 36, times the probability of pulling a red face card, which is 8 out of 52. Okay? The Black King's probability of a large prize, theoretically, is 10 out of 36 times 2 out of 52. Right? I can do this quickly on my calculator, which I plan to do. Let's see. 10 divided by 36 times 8 divided by 52. Comes out to be, probability of a small prize is going to be 0.0427, which if you want to know the percentages, it's 4.27%. So out of every 100 people that play the game, 4.27 people will win a small prize, theoretically. And in this case, 10 divided by 36 times 2 divided by 52 is 0.0107, or 1.07%. So nearly only one person will win a large prize if 100 people play. Now, here's where it gets important, okay? We also have to conduct an experiment. So what we're going to do is we're going to also conduct an experiment of the same thing. I'm going to roll 2 dice 50 times. If my sum of dice is more than 9, I'm going to also draw a card. Okay? So, I rolled an 8. That's a loser. Alright? Now I'm going to keep track of this. Rolls. This is an experiment. Keep track of rolls. Less than 9, greater than or equal to 9. I got 1 less than 9. Now I rolled an 11. There's 1 greater than 9. Now I get to draw a card. I drew a red 3 diamond. Guess what? I have the red face card or a black king. I lost. Card. Lose. Red face card. Black king. I got to lose. Okay? I'm going to roll again. I got a 6. Less than 9. That's a lose. Right? 8. Less than 9. I'm going to lose. I'm going to keep doing that 50 times. Whatever I'm going to find out, what's important is right here. How many got the red face card and how many got the black king? Because this is a small, this is a large. Let's say out of 100, or 50, let's just say out of 100, we got, I don't know, 12 red face cards and only 1 black king. So in other words, we had to give away 12 small prizes and 1 large. Okay, so here's what you need to do. We need to use this information and this information to determine how much it's going to cost us to give away those prizes. So you'll go online, find, let me erase here so you can get a little room. Find 2 prizes. I don't care, plush dolls, teddy bears, whatever you want to call them, slap hands. Find something cheap, okay? Not really cheap, but cheap, because they're only paying $1 to play it, but they need to have something worth their money. It's got to be at least worth $1, okay? Small prize doesn't have to be worth $1. let's say you got a little plush baseball or a plush coin or something, okay? So, small prize got a cost of $1, or no, 50 cents, okay? And a large prize, and this is what you need to do. You need to go online and find these prizes. You're going to find out that these prizes are going to actually be bulk cost. You're going to have to buy about 100 of these. I'm not making you buy them, I'm saying theoretically. You have to buy 100 of these to get the price you need. You can't just buy one, okay? But how do you determine the cost of a product if you buy 32 and it costs $100? You divide $100 by 32, right? If you have 100 in it, it costs you 75. Divide 75 by 100 and it gives you the cost per item, okay? This is cost per award or prize, cost per prize, okay? Small prize is worth 50 cents, okay? Let's say you go online and you find a large prize that's worth $2, okay? So you double your money back in prize, okay? Well, here's the deal, though. You have to understand something. You have to do this for both experimental and theoretical. But this part is the same for both. When you find those prizes, you have to cite your source. Cite the source where you got your information. So let's say it's $75 for 100 items. All right? That means they're each 75%, or 75 cents each. Okay? Because you divide 100 into $75 and it gives you 75 cents. All right, well in this case, we found our prizes. Small prize is 50 cents, large prize is $2. Okay, from experimental probability, if we had 100 people play, we got $100, right? So $100 because it's $1 to play. 12 small prizes at 50 cents is $6. One large prize at $2 is $2. Total expenses $8. All right, now think about this for a second. If we know that profit is revenue minus expenses, we need to know what the expenses are and what the revenue is. Revenue is $100. Expenses is $8. So the profit is 100 minus 8, or $92. Now that's just on experimental. What about theoretical? Theoretically, we're going to have 12 people out of 100 win a small prize and one person win a large prize. Okay? So profit for the theoretical, same $100 for the same people, minus 12 times, well, this is experimental. Let's do, here we go. Theoretical. We got 4.2%, which means 4.27 people out of 100. We'll say that's 5. 1.07 out of 100, we'll say that's 2, okay? So we got 5 people that won the small prize at 50 cents. So 5 times 50 cents is what? $2.50. So that's times 50, $2.50. 2 times $2 is $4. Our total expenses for theoretical is $2.50 plus 4, $6.50. 100 minus $6.50, theoretically, we should make $96.50. Okay? That's it in a nutshell, folks. Now, here's the easy part. Knowing how to do this is not hard. Putting it all together is not hard. To make bonus points is not hard. Here's how you make bonus points. If this is how much money you would make experimentally and theoretically out of 100 people playing, how much money can this company make if they buy the game and put them out at different carnivals for every weekend of the summer? All we're doing is using ratios, right? 100 people play, let's say 100 people play per hour, because you have 2 games running at the same time, okay? Side by side at the booth. All right? So 100 per hour. The carnival's open 10 hours a day. That's 1,000 people playing the game, right? 1,000 people playing the game. 2 days a weekend, 4 weekends a month for 3 months. So that's 2,000 times 4, which is 8,000 times 3, which is $24,000, right? So, for the whole summer, 100 per hour, 10 hours per day, 2 days per weekend, 4 weekends per month for 3 months. Now that seems hard, but it's not. 100 per hour times 10 hours, that's 1,000 plays. 2 days, that's 2,000 per weekend. 4 weekends per month, that's 8,000 per month. For 3 months, that's 24,000 plays. How much money would we earn? Profit-wise, you got $24,000, and you're only playing out how much? Well, if we give away $6.50 for 100 plays, we just have to multiply $6.50 times 10 times 2 times 4 times 3. Same thing we did for this. And we can find the expense. So, for theoretical probability, oh, that's 93.50. I don't know why I said that. We can just do the profit for, we don't even have to do the expense. We can do it. We can spread it out. But we can find the profit, which is 93.50, and we multiply by 10, by 2, by 4, and by 3. Our profit for the summer is $22,440. Now, of course, you'd also have to put down that there's also the expense of paying someone to run the booth. But if they bought, here's another thing. So this is just one booth. What if they bought 3 booths for the different carnivals they got running? 3 times that profit. Explaining that is how you convince someone to buy your game. Okay? Marketing it by the amount of profit that they could possibly get. Potential market. Potential profit. Those are very, very important. You have theoretical and experiment. From my experiment, I found out that it's actually a little worse than the profit's not as good. It's about $1.50 less than theoretical. But, you know, experimentation still shows a 90%, 92% markup on what you're paying for this. You're just blowing it out the water. You're making so much money it ain't funny. That's pretty much it for this whole thing. If you recall all of this, these rules, don't use these specific rules, use your own rules, make up your own rules. It's great. Now, I'm going to know if you do this because I did this. Alright? You can use spinners too. I've got spinners.
Can we take a picture of it as
Sure.
an example?
Yeah, sure. Absolutely. Take a picture as an example. I would use whatever you did in part 1 as part of your part 2 because it's easier to use it.
Are you going to post the video so we go back and look?
I am. I'm going to do it right now.